Till now what we have done, we have first discussed that why one needs StatMech, one needs statistical mechanics, because we, putting bluntly, we cannot even solve a three body interacting system, that means 3 Lennard-Jones particles we cannot solve. Boltzmann solved in dynamics with great difficulty and lot of approximations the 2 body problem. In equilibrium StatMech, 2 body problem becomes equivalent to a quadrature, which can be done in computer, but in simple problems like Lennard-Jones we cannot even do that analytically. So this is one reason that one has to have statistical, that is a technical reason, and there is a more profound conceptual reason, is that even if we could solve Newton's equation for all particles, Avogadro number of particles, what do we do with that, because that contains lots of irrelevant information. This term in statistical mechanics, what is relevant and what is irrelevant, is an extremely important concept. We have to extract from lot of things that are going on something which we observe in real world and also what is experimentally accessible. Okay. So having said that, so that was the difficulty Boltzmann, who was motivated by Maxwell's velocity distribution, to introduce the probabilistic description. He took it halfway, but he couldn't do very far. As I said, other side of the Atlantic, our great Willard Gibbs realized that there could be a different way of doing the things. Willard Gibbs did completely equilibrium statistical mechanics, this has to be understood clearly, while Boltzmann was trying to do transport properties. Even today, transport properties of time dependent statistical mechanics starts with Boltzmann's kinetic equation. So this is a very important distinction one makes. So Willard Gibbs realized that that many different systems which observe, they have same macroscopic properties, they must be in different microscopic states. So it is different microscopic states of the system that belong to a given macroscopic state, then there must be a way to look into equilibrium distribution in terms of a probability. So the important breakthrough then came going from the trajectory or time dependent StatMech or time dependent distribution function, which gives time averaging. From there one wants to go to an equilibrium distribution. So Willard Gibbs realized that the simplicity gates in doing the equilibrium distribution, that could allow him to do a probabilistic description, and he was by that time, early 20th century, his book was published I think 1903. By that time probability theory was well developed, mathematics of probability theory, central limit theorem and all other things were well developed. So he had now he could rely on that. So he then said, if I want to describe a probability distribution, then what are the probability distribution I want? I want a quantity which is I could talk in terms of thermodynamics, in terms of entropy, energy fluctuation, these kind of quantities. He already had one result in front of me, which is Boltzmann's definition of a function entropy. To what extent that entropy, already thermodynamics was rather well developed, entropy function or heat function was well known. That correspondence had occurred to Boltzmann, I am not too sure of, but probably it was, but certainly Willard Gibbs realized it. So he had that formula, A is equal to KB ln omega, KB is Boltzmann constant, very appropriately put there. And so now he had to find the omega, and of course if it and rest of the thermodynamics. How did he go about it? So he said, okay, let me construct an ensemble which is a huge collection of the systems. Each system has characterized by same number of particles n, same volume V and same energy, all are constant. Now and then in this ensemble he said, okay, how can I describe now probability distribution? He then introduced 2 postulates. One is that he wanted to do the average. How do I do the average? Instead of one way to, of course, time average, follow one system for a very long time. The other one you follow many identical systems. Now the idea is that many identical systems, billions and billions of identical systems of NVE, they are all in different microscopic states. Why? Because number of microscopic states is enormous. It is billion to the power billion. So all these systems will be in different microscopic states. So that is a very critical understanding, that I can construct an ensemble, means a collection of identical particles, all of them in different microscopic states. Then if time averaging, that I do by following in one system a trajectory for an infinitely long time or very long time, that can be replaced by averaging over these different systems. Lo and behold, what is the advantage? Instead of following the trajectory, which is a time dependent quantity, I am going to talk of something which is time independent, and that is the enormous simplification. I do not have to solve Newton's equation anymore, which was the prescription of Boltzmann. Then when he did that, of course, he had this ensemble picture of systems in different microscopic states and averaging over them is what is today is Monte Carlo simulation. Trajectory is molecular dynamics simulation. However, in order for the trajectory to be equivalent to ensemble I have in all different microscopic states. You have to understand, these are still at a conceptual level. Things are assumed, these are postulates, and the verification comes, with the results and comparison with the experiments. Then he said that, okay, my trajectory then must go to all the microscopic states that I am representing in ensemble. Then comes the second postulate, which is called equal a priori probability. That means all microscopic states are equally probable to be visited by the system, and in a long trajectory they will be visited equal number of times. These are limiting things: infinite number of states, infinite time, infinite number of systems. So everything asymptotic, where things can be proven exactly. Now, when I say things could be proven exactly, that of course happened only in 1980, one case, more than 100 years later almost. So these things, that a system equally probable, but equally probable does not mean that it will be visited. So the two things I jumbled together to be separated, that comes as a hypothesis that all these states will be visited. That is the ergodic hypothesis, that each state will be visited in the course of time. That means its system will not get stuck in a minimum. That haunted us in molecular dynamics simulation. That is why you cannot do phase transition just in NVE, because it gets stuck in one minimum. Then all the new techniques like umbrella sampling, metadynamics that have been invented and created are essentially to take the system out. So the reason that one has to be conceptually clear and study these things even more now than before is because of the connection with the modern StatMech, and which is so powerful now. It is reaching the state of quantum chemistry in this sense. The packages are being available. I see my students or other students getting, like one of my students without understanding too much got great results in rotation of carbon monoxide, nitric oxide and cyanide ion in a aqueous binary mixture, something which was unthinkable few years ago, such complex system, but that can be done now. I cannot claim that the student knows very great of the concept of statistical mechanics, cannot do coupling theory analytical work, but the results are at the hand, and at the end of the day results are that are important. That is what everybody wants from you. So statistical mechanics has come to that level now. So we have to understand this little bit more detail to have a certain sophistication in our understanding, sophistication in our. So then from that microcanonical ensemble, using S equal to K ln omega, we derived the expression of pressure, expression of energy, ds dt is energy. So everything is now number of omega, number of microscopic states omega. Well done, that part was done. But then NV is a very artificial system, because it is a system which has same number of constant number of particles, which is not changing, constant volume, constant energy. That is not the real system. Real system which volume is fluctuating, phase transition, ice, melting, density goes up by 10%, Then you have the energy fluctuating, because these systems are far more open in at least in chemistry and physics, and in chemistry we have also systems where chemical reaction taking place. So N is changing. So NV microtransmission is too restrictive. So the next stage, Gibbs did construct a beautiful and brilliant mental construction that he went over to constructing a super system out of NVT, where energy exchange allowed. He put all NVT together, allowed interaction between them, flow of energy, then put it whole thing in a bath, let it be equilibrate, then put an insulator around them, so that the whole super system is an NVE of, if italicized N is my N number of particles, then italicized N by normal N, italicized N by V, italicized N by E are the number of particles, volume and energy of my super system. Now he formed a microcanonical ensemble of the super system, and then showed by doing constant method of constant variation or Lagrangian multiplier, we can get a quantity called partition function, whose logarithm gives free energy and whose derivatives gives all the thermodynamic properties. After doing that, he was a genius of highest degree. He didn't waste time in seeing movies or other things. He was single and he was always coming back and forth from Starling laboratory. Probably he had all the time, but it's amazing what he did. He did the grand canonical ensemble, where now number of particles also exchange allowed. The same thing was done, and he wrote a beautiful expression of equation of state, PV equal to KBT. We remember all these are energy dimension, PV equal to KBT NN grand canonical partition function. Then we also discuss NPT, which is used most in simulation and experiment. So till now we have done all the groundwork, still keeping things fairly simple. We have done 4 ensembles, and we could have spent more time on NPT, but okay, that is I told you that it is essentially same construction, but the thermodynamic potential of NPT gives free energy. So thermodynamic potential of microcanonical is entropy, thermodynamic potential of canonical is Helmholtz free energy, thermodynamic potential of grand canonical is PV, and thermodynamic potential of NPT is gives free energy. That what exactly thermodynamics tells us, that exactly comes out to be true. So one of the major goal of statistical mechanics is to explain thermodynamics. Remember, one of the things that you read in thermodynamics, I don't know, we had a great teacher, Professor Mihir Choudhury, who again and again told us one thing, that thermodynamics cannot give you anything a priori, give the results, it gives certain relations. So thermodynamics does not give you what is the value of entropy, it cannot give it unless of course you integrate over CPT. It does not give, so that means there is no, it is not a theoretical machinery that gives you anything from first principles. That's the correct statement. It doesn't have first principles. It has certain working principles which we call laws of thermodynamics, which will be fun to teach sometime, the thermodynamics in a very deep and fundamental level, because that's a wonderful subject. However, here we don't pay for that time or course content for that, but here thermodynamics then comes out of statistical mechanics. So one of the first idea of statistical mechanics was to explain thermodynamics, and what it does in a beautiful way, starting from microscopic principles, intermolecular interactions which gives you energy levels, then everything flows, you get all the thermodynamics exactly. So these are the theories. We are going to do applications of statistical mechanics, and we will do the simplest thing first, which is monatomic ideal gas, monatomic. So these two things are both very important. So this is what we are going to do, and it is an extremely illustrative and very, very nice. And I saying when we studied these things we thought it is useless, but then later, much later, when I did Bragg-Dien intercalation. Okay, so we will do this is the following thing. What we will do today: derivation of the thermodynamic equations applying principles of statistical mechanics. These to derive microscopic expression, model system we will do now. Entire volume available to all the molecules, maximum translational entropy in ideal gas. This is a very important thing again, because just in a bark I gave the lecture where I had a path which is diffusion and entropy. There is a very hot topic now, even in active matter everywhere, diffusion and entropy. What is the role entropy plays? and okay. So what goes in there, the entropy called excess entropy, and excess entropy system minus the entropy of the ideal gas, and diffusion is e to the power excess entropy. You know, it is amazing how these things haunt you, come back to get you the results. So, you know, those of us who thought that ideal gas, monatomic gas is not important, we are using it every day now. Okay. So, let us now do these things. Hamiltonian of this system is any interacting particles is H n TV is equal to n number of particles. So, Hamiltonian is just kinetic energy, there is non-interacting, so there is no potential energy. If they are not, then partition function is just n over integration over all the particles. So, partition function of n number of particles Chinese people did tell, you know, they do not nothing to worry about India because most of the Indians are sick, which I think is by and large true. I myself got sick yesterday. So, this is the configuration part and this is the momentum part, and then these are function of all Rn that we write like that, and function of without writing. So, this is the integration that we have to do. So, n particle integration over n vector of 1 to n momentum of n number of this, and this is the Hamiltonian. Then I hope you understand, this is very important because this will be repeated again and again. It will be repeated today and it will be the important class that will start on Wednesday morning with the Mayer's cluster expansion theory. We will use this again and again and again and again and again. Okay. Momentum 3n integral here, 3n integral here, and this is the Hamiltonian. In my case, Hamiltonian is just kinetic energy, and then you can see this will come out straight with a, since this is additive, I can have to the power n. I hope you understand, additive means it's just multiplication. This is the thing. Is it clear, this thing how it is happening? Because this will happen again and again, that's why I am spending some time here. What we have done, that since this is sum, all of them have the same mass. Now I can write it as a product, and then the product means there is a n number of them. Okay. This will be h to the power 3n here. That has been missed. We have to put that back. This is a indistinguishability called Boltzmann's factor. He put it by hand. Then quantum mechanics came. It became okay. The basic idea is that you don't get an extra state but just by exchanging two particles in the, by keeping everything identical. So permutation factor is this time, and we have h to the power 3n, and there is a great new reason for h to the power 3n. Anybody can tell why h to the power 3n should be there and must be there? A very nice and elegant, very simple explanation. You guys did take StatMech course, no? Yeah, absolutely. It is close to the answer. Real answer that it has to be dimensionless quantity. See, we put log in front of that. You cannot have a dimensional quantity after log or in exponential. There has to be dimensionless. That's the first thing. We usually ignore that fact very much. Second, that we actually normalize the volume integration by the volume in the cell, and the volume in the cell is given by Planck's constant. And if you do that, this quantity, that Q is one of them. So let me say let me also put it here, H3n n factorial. Then now dr1 dP1 e to the power minus beta P1 square by 2m, the whole thing in the exponent. This is to the power n because the n particles there. Okay. Now, this is volume, this is momentum. Okay. Now, if I make now this is L cube, this is momentum cube. If I make length in momentum, then what is the dimension of length momentum? Okay. So, length and momentum, so dimension of length, dimension of momentum is ml by t, right? Yes. So, this is the dimension of, this is also the dimension of the Planck's constant. So, the momentum L by T, ml by T, energy is ml by T square, ml square, right? That is what I was saying, something is missing. I was mumbling, ml square. Now, in Planck constant, remember h omega is energy, that is ml square by T square. Okay. That means we are having, that is why h, dimension of h bar, if this one t goes out, right, you get ml square by t. This is also called the dimension of the action. So, that is the volume in the phase space, which is normalized, there should be h to the power 3 n here. Okay. Now, we most of the time do not write it, I actually do not like to write that one, but it is okay. This is the dimensionally correct one has to be. So, now one does this integration of one particle, this is a single particle, that decomposition is possible because this is non-interacting. When you do that, then dpx, dpy, dz, dx, dy, dz, d minus beta h. So, one of them, this one gives volume, so that volume comes out, then this integration is same integration because next decomposition comes p momentum square same as px square py square plus pz square, right, and px square py square pz square. So, this integration is this one. What is this of this integration? Value of this integration? Root over pi by a. Yeah. So, root over pi by a means this is 1 over kbt, 2 here, m here, 2 pi m kbt, right? Root over pi by a, both are a, this also comes here, yeah, 2 pi m kbt. So, this is the integration. That integration in its full glory comes here, and this, since it is root over 3 of them, 1 to 3 of them becomes cube, and since root become 3 by 2, if I have to put Planck's constant h to the power 3 n here, that goes here at h square. Okay. So, this is the small cube. I have to 1 over n factorial in front of the big cube. This is the partition function of the monatomic gas.